Hello everyone. This is the fifth video under lecture series on linear transformations, and in today's video I'm explaining what is rank and nullity of linear transformation. So in the last video I defined what is kernel of a transformation and image of the transformation. Suppose if you have a transformation T from a vector space V to a vector space U, kernel of T is a subspace of V, that is nothing but which maps all those elements to 0 of another vector space U, and image of T is a subspace of U, so the whole vector space V gets mapped to some subset of U, then that forms the image of the transformation. This is image T and this is kernel T. Kernel of T is a vector space over the same field as V is a vector space over that field, and similarly image of T is also a vector space over the same field as that of U. So if they are vector spaces independently, so if kernel of T and image of T are subspaces, they are vector spaces independently. So if they are vector spaces, then those vector spaces will have a basis, and number of elements in basis is called as dimension. So we have here kernel of T and image of T. These are subspaces. So if they are subspaces, they are vector spaces independently. Vector spaces. So if they are vector spaces, they should have basis and dimension. So these two vector spaces, they have basis, and dimension means number of elements in the basis. So what is dimension of kernel of T? So dimension of this kernel of T is called as a nullity of T. Nullity of this transformation. Similarly, dimension of image of T is called as rank of the transformation. So nullity of T can also be denoted as eta of T, and rank of T is rho of T. Okay. So dimension of number of elements in the basis of image of T is called as rank of T. Number of elements in the basis of kernel of T is called as nullity of T. Okay. And this leads to rank nullity theorem. Rank nullity theorem, which is also called as Sylvester's law. Rank nullity theorem says that if you have a transformation T from V to U, then dimension of kernel of T, that is dimension of kernel of T plus dimension of image of T, which is equal to dimension of V, the first vector space, that is rank of T plus nullity of T is equal to dimension of V, dimension of this first vector space. So this theorem or this law is called as a rank nullity theorem. And you have to remember or one more theorem, that if you have, if span of V1, V2, so on up to Vn equal to the vector space V, then span of T of V1, T of V2, so on up to T of Vn is equal to image of T. That means if you have a transformation T from V to U, linear transformation T from V to U, and there is a set which spans the whole space V, spans the whole space V means every vector of V can be written as a linear combination of these vectors, then the image of T, image of the transformation, is spanned by T of V1, T of V2, so on up to T of Vn. If T is a linear transformation, then images of these vectors, spanning vectors, spans the image T. That is, image of T is a subspace. This subspace is spanned by the images of these spanning vectors. This fact you have to remember, that helps you to find out the dimension as well as basis for the image space. Let us illustrate this with an example. See here, let me take up the same transformation which I had explained in the beginning. T is a transformation from r square to r square, rotating a plane by 90-degree clockwise. That is, goes to y comma minus x. You know that what is the kernel of this transformation? It is a set having only 0 vector. Okay, only 0 comma 0 gets mapped to 0. No other vector maps to 0. So kernel of T is equal to set containing 0 comma 0. And image of T equal to, you know that it has all vectors of the form y comma minus x belongs to r square, such that x comma y belongs to r square. Okay, there exists x comma y in the domain for which t of x comma y equal to y comma minus x. So this is how the image is. Now dimension of kernel T is called as nullity of T. Dimension of kernel T is equal to nullity of the transformation, which is eta of T, which is equal to 0 in this case, because it has only 0 vector, not counting number of elements in this. Whenever you know that whenever a set has only the 0 vector, then its dimension is always considered as 0. Okay. Now image of T is nothing but here, how to simplify this further. So this is y into 1 comma 0 plus x into 0 comma minus 1, such that x comma y belongs to R. I can simplify it like this. Okay. So this is equal to, because there are no restrictions on x and y, hence there are no free variables. Each variable involved has to be simplified like this. Y into there is 1y, no y in the second coordinate, plus x into there is no x in the first coordinate, the coefficient of x is minus 1. That means what? These two are linearly independent vectors. So this implies image of T is spanned by the vectors 1 0 and 0 minus 1. Span of this equal to the entire space image of T, and they are linearly independent also. So dimension of image of T equal to how many elements here? 2. So that is nothing but rank of T. So dimension of image of T equal to 2 is nothing but it is same as dimension of R square, means image of T equal to R square in this case. So means every vector of R square is having the pre-image. So we got here rank of T equal to 2. Therefore, you can verify rank nullity theorem. So rank nullity theorem, as per that, rank of T, that is 2, plus nullity of T, that is 0, equal to 2. Is it equal to dimension of V? So dimension of R square. It is equal to dimension of R square. Hope you understood this example. Similarly, let me give one more example. See, consider the projection map T from R cube to R cube, which is given by T of x comma y comma z equal to x comma y comma 0. Okay. So this is the projection map. So we have seen in the last video, kernel of this projection map equal to kernel of T equal to set of all vectors on the z axis. Z belongs to R. Correct. Now because entire z-axis collapses and it is mapped to 0, means here you have t of x comma y comma z equal to 0 comma 0 comma 0. Which vectors are mapped to 0? X comma y comma 0 equal to 0 comma 0 comma 0. So this implies x equal to y equal to 0. This is equation of z-axis. So entire z-axis gets mapped to 0. So that is kernel of T. Now let us see what is image of T. Image of T, all those vectors of the form x comma y comma 0, such that x comma y belongs to R. So this is nothing but xy plane. Z coordinate 0 means it is xy plane. So I need now dimension of kernel of T. So which is equal to, see here, kernel of T can be simplified as z into 0 comma 0 comma 1, such that z belongs to R. So there is only one linearly independent vector. So kernel of T is spanned by this vector. This one vector spans the entire kernel of T subspace, and it is this one single vector, non-zero vector. It is single vector is always linearly independent. Therefore 0 comma 0 comma 1, this is basis for kernel of T. and dimension of kernel of t equal to 1, because there is one vector. It is non-zero vector. Whenever you have a non-zero single vector, then you can take the dimension of that as 1. If you have a zero vector, you should remember dimension of that is always equal to 0. So I got dimension of kernel of t equal to 1 here, 1, which is nothing but nullity of t. Next, I need dimension of image of t. Now look here. How can I simplify this? Two variables here, x and y. So x into 1 0 0 plus y into 0 1 0, such that x comma y belongs to R. This is how image of t can be simplified. Correct? No. So now the entire image of t is a linear combination of these two vectors, and you know that these two vectors are linearly independent as well. Therefore 1 0 0 0 1 0, this set spans image of t, as well as this set is linearly independent. Therefore this is basis of image of t, and number of elements in the basis is 2. Therefore dimension of image of t equal to 2, that is rank of t. Now verify rank nullity theorem. Rank of t plus nullity of t equal to 2 plus 1, that is equal to 3, which is same as dimension of R cube. Dimension of R cube is 3. Hope you understood how to do this. Now we can use the proposition which I had stated in the beginning. The proposition was, if span of these vectors v1 v2 so on to vn equal to the entire space v, then span of the image vectors t of v1 t of v2 so on up to t of vn equal to image of t. Means image of t is always spanned by the images of these spanning vectors. Let us check that. You know that now v equal to r cube, correct? No, v equal to r cube. Therefore, which vector span this r cube? 1 0 0 0 1 0 and 0 0 1. These vectors span of these vectors equal to r cube. Now, what is the span of images of these vectors under this transformation? What is t of 1 0 0, which is 1 0 0? What is t of 0 1 0? That is 0 1 0. What is t of 0 0 1? T of 0 0 1 is 0 0 0. So that is equal to image of t. Image of t is spanned by these vectors. You know that in a spanning set, if there is a 0 vector, it is same as a span of these two vectors, because 0 vector doesn't contribute to the span of any set. It is same as the span of these two vectors. Therefore, span of 1 0 0 plus 0 1 0 equal to image of t. So how many, and you have to, this is comma, and you have to check, are they linearly independent? Yes, you got the same thing back here. Okay, so this is image of t is spanned by these two vectors, because those there is 0 doesn't contribute to the span of these two vectors, because lambda into span means linear combination. Lambda into any value, it is 0 only. Therefore span of these three vectors is same as span of these two vectors. Hence this spans the image of t, as well as these two vectors are linearly independent. Therefore dimension of image of t equal to 2. See here, without simplifying it in this way, I can apply the proposition also. I had stated the proposition earlier that if span of v1, v2, so on up to vn equal to v, then span of images of these vectors, span of t of v1, t of v2, so on up to t of vn, that is also equal to image of t. So you know that now v is equal to r square. So which vectors span r square? You can take the standard vectors 1 0 0 1. This spans the whole space r square. Now find the images of these two vectors under the transformation. What is t of 1 0 and t of 0 comma 1? T of 1 0 is 0 minus 1 and t of 0 1 is 1 0. Therefore, span of these two vectors 0 minus 1 and 1 0, that is equal to image of t. The same thing we got here, 1 0 0 minus 1. So these two vectors spans the whole space image of t, and you know that these two vectors are linearly independent also. Therefore, these two vectors form basis for image of t. So how many elements in the basis? That gives you dimension of image of t equal to 2. You can do it in this way as well. This is how finding rank of a transformation and nullity of a transformation. But this method won't apply for all kind of transformation. When the transformation is simple, you could take those variables outside, and you can get the dimension and the basis for a given transformation. So when the transformation is like this, if for example f of x comma y comma z comma t equal to x minus y plus z plus t and 2x minus 2y plus 3z plus 4t comma 3x minus 3y plus 4z plus 5t. So in all such cases, when the transformation is a little more than the simple, so in such cases, how to find out kernel of t? What is kernel of t? Where the transformation maps all vectors to 0 vector, that you have to find out. Then you will get set of equations. There comes the application of a system of equations also. Similarly, you have to find out image of t, which vectors spans the whole space, that you have to find out. So it is not as simple as we have done with these two transformation. One was the projection map, and another was the rotation of a plane by 90 degree. So that doesn't apply in these cases. So how to do that? So I will make a separate video on how to get basis and dimension of kernel of this kind of transformation, as well as image of this kind of transformation. And one more fact is that you know that every transformation is represented by a matrix. Similarly, every matrix can also be viewed as a transformation. So in the next video, first I will explain how matrices represent a linear transformation, and you can find the kernel and image of matrix mappings as well. So you were finding usually rank of a matrix and nullity of a matrix, null space of a matrix, rank of a matrix. Then it is same as finding the rank of and nullity of the given transformation, because every matrix can be viewed as a transformation. So and hence we find rank of a matrix as well as a nullity of a matrix. That I will explain in the next video. Hope you understood how to find kernel and dimension of a kernel T, and dimension of the image of T for simple transformation. That is the conceptual understanding. Now I'll extend that to the more general linear transformations. Then I will explain how to do matrices as a linear mappings. Thank you for watching.